In previous video, we saw the conservative form of nonlinear equations in fluid mechanics. This equation was a continuity equation and still it is a continuity equation in one dimension. Then we have momentum equation. And if we write these two equations in a matrix form like this, then such form is called conservative form. This is a very famous concept or very important concept in finite volume method. When we write equation in column vector, the quantities, these are our solution, these remain conserved. And we will talk about that in future when we discuss numerical methods. So in this video, we will talk about the Jacobian matrix. Most of you probably know that what is Jacobian matrix, but how it arises from these two equations, or not only for these two equations, but many other equations. So this video is dedicated to learn about the Jacobian matrix. Let me just go back to the advection equation, which is written like this: partial by partial x, and there is a flux function q. And you know that when we keep this flux function q is equal to u bar q, remember that here this q is a scalar quantity. When we put this value, this flux function over here, we get partial q by partial t plus partial by partial x. U bar q is equal to 0. And we learn about that partial q by partial t, that u bar can come outside of this derivative since it is a constant. So we can write u bar partial q by partial x is equal to 0. So this was the advection equation. But I don't want to teach you derivation of advection equation from this logic. Let me just erase it and go back. Suppose that we have the same equation where we want to find out the advection equation, not only advection equation, but many other equation. So when I write it down, this equation like this, for example, we have f is a function of q, and q is a function of x and t. So it means that first I need to take a derivative of f with respect to q, then the derivative of q with respect to x. So what we get? We get partial f by partial q, and then we have partial q by partial x, which is equal to 0. If I just keep f is equal to u bar q, then you can see that if I take a derivative of this f, which is a flux function, partial f by partial q, then we get u bar. So this quantity, this derivative will become u bar. So we get partial q by partial t plus u bar partial q by partial x is equal to 0. So that was the main motivation, that you can write your general form of equation into the advection equation by first considering a derivative of that f with respect to q, then the derivative of q with respect to x, then you get the same answer. Now let me just raise it here. Remember that the q, I repeat, is a scalar quantity, Now I move back and raise it down. Now suppose that we have a vector quantity. For example, if I write these two equations like this, partial q q vector by partial t plus partial by partial x, f is a function of q vector, and that will be equal to 0. And we know that what is q vector. Uh, just to emphasize one very important point over here, this q vector, there is a vector sign over q. The reason is q is a column vector. But you know that in linear algebra, we do not use vector over like this, like vector. Okay, so I have putted this vector over the variable q just to show you that it is a vector quantity, and this q vector is defined over here. Okay, I hope you got the answer. Now we follow the similar procedure that we already introduced. It means that partial q by partial t plus partial f by partial q vector, and remember that f is also a vector quantity since we have two components. And just to emphasize again, f is written as a bold, so it is a vector quantity. Partial q vector by partial x is equal to 0. What you can see over here, this is called in one dimension, it was just a derivative of f with respect to q. Okay, but here, since f is a vector and q is also a vector, so f has two components. F is equal to f1. Let me just write it over here, f1 and f2. And similarly, we have q1 and q2 like this, these two terms. So it means that for partial f by partial q, we required partial f1 by partial q1, partial f1 by partial q2, partial f2 by partial q1, partial f2 by partial q2. All these derivative, when we put this into the matrix, this is called a Jacobian matrix. So the Jacobian matrix is the generalization of a derivative of a real valued function. So in future, we will talk about that the Jacobian matrix in different perspective. Thank you for watching.